see how that works. Okay, did everyone out there hear that? Then in the future, I could set it so they can personally record if they want.
Yes, sir.
And then you can show me how to do that. All right, that's fine.
And 2012 doesn't have the switching issue, so it's good to go.
Oh, great, thank you, thank you. Okay, did that, I don't know if you overheard that short conversation regarding the recording part of it?
Yeah, sounds good.
Okay, then that will be the plan. Hopefully the upload to the cloud will work, and like I said, he said that the conversion to MP4 is done in the background, so I don't know. So, but he seems confident it'll work, so I can get with him and we can post it afterwards. So it'll be available. Any other good questions?
Right. Sir, Dr. Pieper,
Mm-hmm.
can you read the chat by any chance? In case we want to ask questions through it without interrupting you, maybe through like just typing? Yeah,
okay, I got the chat. Why don't you send a quick chat, a question over and see if it works. Sometimes it shows, sometimes that bottom bar seems to disappear and sometimes it shows up. But go ahead and send something over and see if it pops up, then I'll see it. Otherwise, I don't know if it's working correctly or
not. I have sent it.
Okay, well, I'm still waiting for something to pop up on our side. Maybe somehow my settings. Let's see if I can catch him. I don't know why I have not seen the chat option produce anything. Let me click on chat, see if anything's there. Okay, now when I push on it, I see this. Actually, interestingly enough, I see students that are logged in or took the invitation. But I cannot tell from here, there was a question submitted on chat. So let me see if I can grab the guy next door if he's still, wait. I do see there's one chat, something showed up there, but how do I know who it was? Maybe.
It should have the names from something to everyone.
It does. But it doesn't show me immediately what that chat message was. Just has the list. And for most of them just almost the same. The only thing is it seems to indicate you're currently talking and I'm currently talking and no one else is. But other than that, I don't see the question. Let me see if I can click on it. Click on that.
Are you under participants?
He's
because
the host.
On ours, well,
can you see the screen? Can you see the screen that says review at the top?
Yes, sir. We can see the screen.
Okay, then that's good. Of course, this was intended. Now, as far as your question that has me, okay, here's one. I think this is a chat message, right? From Corinne, right? Corinne.
Yes.
So I saw that one. So when I come over here to Zoom group chat, I see that question, and I can.
Okay, that is fantastic.
So I think that part's working. So I'm going to leave that window. Hopefully that window won't go away on its own or time out. I'm going to leave that over on the side, and then we can just go ahead and. Okay, well, thanks for that, and I think that may prove to be helpful to be able to see those chat messages.
Sounds good.
Okay. Anything else?
Yeah, exactly where are we starting at in your notes?
Good question. We are starting at the review part actually begins with the notes on chapter 5A, which we had started. But it goes through the first 6 pages briefly. It just summarizes what happens in the material we covered. And then after that, the chapter 5A notes will pick up with stuff we had not covered in more detail. Does that answer your question? Not hearing anything, so. Okay.
Yeah, sorry. I was in a different window. Yeah.
Okay. So I'm going to just go through, like I said, I have a couple pages that would come under the category of review, which is intended to summarize the initial pages in Chapter 5A. And we'll see how that goes. And if you have a question, I think we can get it and hopefully answer it. Okay. Okay, to start off, the Chapter 5A deals primarily with this topic, which we might call performance measures. And to kick things off, we have to draw from a result that we obtained in Chapter 2 for the unit step response under the conditions of underdamped and all the initial conditions set to 0. So the input of being the unit step is the sort of the driving force or energy for the system response. And we derive this in Chapter 2, so we're taking it right from Chapter 2. And the performance measures that we actually start on included the peak time for the first peak, the percent overshoot, and a quantity that we really didn't get into called the settling time. Now, to summarize how we went about this without going through the details all over again, we realized that there's a sketch on page 4 of the notes that we refer to. And here's page 4 of the notes. And in referring to this sketch, we were interested in getting the time at which that first peak occurred. And that's actually T1 there, I believe. So that's our T sub P where that first peak occurs. And so we realized that these are all like, in the vernacular of mathematics, critical points. But we also realized that we're only interested in that first, and it is a maximum, right? So that would be the n equal to 1 case. And so since they're critical points, the way we proceeded was pretty much consistent with your experience and understanding of calculus, is that we would be forced, or we would not forced, but we would take the derivative of the function and set it equal to 0, and then ultimately by solving for that equation for the possible times that create that condition, we get our times at which we have critical points. Okay, so in the end, what we came up with after a fair number of steps, including taking the derivative, was this condition would be the condition you would need for the various critical points. Then if we set the n equal to 1, remember the picture. If we set the n equal to 1 and solve for that condition, then we would set the t equal to t peak. Now we're specifically identifying that peak. And this condition popped out. Okay. Any questions so far? Not hearing anything. Okay.
Are we on chapter 5?
This is chapter 5.
Okay.
So then what we did was we used the fact that we had the specific time at which that peak occurred, or at least a condition identifying that time. And we used it in combination with the formula for the y of t, of course, that which presumably that identifies the specific time. And so therefore, if you put t equal to t sub p, you should get that peak. And after some steps involved, we came up with an expression for that what that peak would be, peak value, and it turned out that formula there was the right one. It involved the damping ratio and the beta, which is related to the damping ratio. And then also the beta could be written in terms of, because it's one, the damping ratio is also the cosine of the angle theta. So 1 minus cosine squared is sine squared, take the square root and you get the sine. So we knew that was connected to the sine. So this turned out to be a compact way to represent where the value for that peak. Okay. Any questions? I know I'm summarizing a lot of steps, but we did cover them in class, and it's in the notes. Okay, so now the idea is that one of the performance measures is what was called the percent overshoot. Okay, and that's percent overshoot would be like the percent over the final value. And the idea would be that if in fact you went back up here and you let t go to infinity, the final value would be 1. So the 1 is the final value, and so the percent is overshoot is relative to the final value. So in order to get that percent overshoot, what we had to do was recognize that take this this maximum value at that point and subtract 1, then multiply by 100. So that became this became our recipe for the percent overshoot. Now, it was mentioned, I'll mention it again because you may have forgotten it, just for clarity purposes, that this is all for, as indicated up here at the top, for the underdamped. So if you're overdamped, you don't have an overshoot, and therefore it's not defined. Again, if you have a question on that, right time to speak up.
Say it again.
Yeah, as we can see, this formula was derived under the underdamped conditions, and the idea being that what we saw in this picture in terms of the behavior of the response is not characteristic of the overdamped, which actually more or less asymptotically approaches the value 1. It doesn't have that oscillatory behavior. So technically speaking, you can't really define a percent overshoot, or it's not defined for the overdamped case. Does that clarify the point?
Yep.
Okay. And so that limits us to the damping ratio being less than 1. Okay, where's my second page here? Okay, so another way which will turn out to be useful for problem solving for the percent overshoot will involve a little bit of translation of that expression, just using trig, but it turns out it turns out to be helpful. And we can replace the damping ratio with the cosine of theta, the beta with the sine of theta, and otherwise it's the same factor here. Now, of course, to get the percent, you have to multiply by 100, but we're just focusing on the factor there, the important factor. And we see, in fact, that since the sine over the cosine is the tangent, we can write it this way. I mean, it's sort of optional if you know, I guess you could put it up in the numerator as a cotangent if you wanted. But I mean, I'm just saying that I find on the average, we're more interested in the tangents, more confident with tangents and cotangents like we used to tangent. Anyway, so here is the another formula for the percent overshoot, which for one problem that's coming up will prove to be useful. And if you remind me when we get to it, I'll explain. It's primarily useful because in a sense, we know that the numerator and the denominator, as we see it here, would both depend on theta, right? And if you have it this way, then you've got the dependent variable theta in two places, or dependent or independent, depends on how the problem is posed. But the point is, you've got it in two places, where if you have it this way, you only have it in one place, and it makes it easier to solve for it. And we'll see that's where the advantage lies. That'll come up later in the example. So we also took a quick look at the percent overshoot, and I guess there's a factor of 100 in here, but what we found out was the percent overshoot will in fact go down as the damping ratio goes up, and we found out that the so-called peak time, in terms of peak time times the omega n, that quantity will in fact go up as the damping ratio went up. And then there's this figure that I think this is getting close to where we finished last time, that we had a in-class lecture, was in fact, we saw that the percent overshoot decreased with the damping ratio, and this product omega n TP increased with the damping ratio. And there's this figure 5.8 that is pretty much a sketch or a plot of that, which was borrowed from the book. Right there. And this is, I believe, if I'm not mistaken, this is where we finished. Anybody want to correct me on that? That's kind of how I remember our last lecture. I'm not hearing any points on that.
Yeah, it seems right.
That's okay, that's good. All right, so where we had not gone before, we're planning to go to maybe today, hopefully, and get there, finish it, and even move on, is this quantity called the settling time. Okay, if you look at it, what we've done in terms of performance measures, we actually knocked out two of the three. We knocked out the peak time. We got a rule for that, and we knocked out the percent overshoot, but we have not yet tackled this, what's called the settling time. Now here I'm switching back to, now we're jumping back into the regular notes, starting on page 6. Okay, let's see. All right. Now, if we look at the function y of t, which is our response that we had on the previous page, we can interpret that in a way that leads us to what's called the settling time. And so I've got a picture here that goes with that needed interpretation. So if let's say here's our function y of t, and here is our response, okay, which kind of looks like my sketch before. Presumably it's more accurate than my sketch. Is that a question? All right. Okay. So now if we look at this, it settles out at the value 1. You can see the overshoot there. But you can also see there's what I have to call kind of a wobble to this thing. So, so we can view the signal as a constant, which happens to be 1, and then a part that's a wobble. Okay. So, so our wobble will be dictated, if you look at it, pretty much all the elements here are repeated here. That would be our wobble, all right? And the idea is, well, we can see that the wobble part actually seems to have an identifiable envelope, which serves as a bound, preventing it, for limiting the extremities for the so-called maxes and minims as you go along. And of course, if you look at this, it's really just an exponential. So in a way, you could argue that what is our decaying envelope serves as our boundaries for this wobble. And so there is our decaying envelope, if you want to think of it, which happens to be a decaying exponential. Now, if you went through and just if you asked the question, well, what does this mean if you said t equal to 0? And I'll let you check if you said sine of theta is equal to, we know is equal to beta. You said t equals 0 here, and t equals 0 there, the exponential is 1. So if you said t equal to 0, that whole wobble becomes equal to 1. Right? And you get, and just like you'd expect, 1 minus 1 puts you right at t equals 0 at in other words, 1 minus 1 is 0, and you're sitting right there. So the observation is that we can see that this bounding envelope part, which is decaying exponential, goes to 0 as t goes to 0. So it is as if you had subtracted 1 from the actual signal, and you get this sinus, what looks like oscillatory is the right term, not exactly sinusoidal, oscillatory decaying signal. Then the idea is that these settling times are tied to a certain standard for how close the response is. No, to be precise, how close it is to the final value in such a way that it never gets outside of that boundary again. In other words, you can see the envelope here sort of serves as a boundary for both the maximums you can have, as well as, and I guess if we have another minimum, all the minimums as well. So the idea is if we can force that exponential, or find the condition for which we know that exponential will never rise above that value after that time, then we can say, well, that will dictate our settling time. Now, maybe that seems kind of maybe a little unclear, but let's see how that would work. We see that again, that envelope part, okay, is a decaying exponential, and we also see that the actual response itself never goes outside of that envelope, either from the positive side one or the negative side 1, okay? So, so the idea would be that once we solve for that condition for, let's say, 2%, and that would say like you're within 2% of the final value, and we know it'll never exceed that after that point in time. You're within 2% of the final value, then if you can solve for that T sub S, that will become the 2% rule, settling time rule, okay? Right time to speak up if you got a question about that. Because that's what we're going to do. We're going to solve for the TS settling time that would be tied to a 2% rule, which means in brief that it's within 2% of the final value. Okay. So at this point, if we're confident on what that means, then we can go ahead and solve for that, the condition for that T. Yes.
Is the 2% rule like a standard?
Yes, it'll become it'll be a standard for problem solving if that's the point of your question, as we'll see.
Yes.
Yeah. See, once we get the 2% rule, then in a lot of problems we won't rederive it. We'll just use it because it'll say, okay, use the 2% rule for settling time. I think that's the point of your question, but I'm not sure.
No, that's correct. Thank you.
Okay. So what we're doing now is just coming up with that 2% rule, which is the rule that is discussed in the text. And I believe you may want to pay attention to the in-between details because one of your exercises that go with this section is to come up with what I call a 5% version of this rule. Okay, so in other words, a 5% settling time rule. So you're within 5% of the final value instead of 2%. So I hate them just say, well, all you need to know is that 2% rule, because one of the exercises will require you to come up with a 5% rule. But the steps are going to be the same. Okay, so so to do that, we want to set this up kind of in a mathematical format that makes it easy, so to speak. So, and again, I'm not sure it's the only way to do it, but it seems like from convenience, let's just go ahead and let X represent, not X like in the coordinate X, but X like as some dummy variable. Let's just let X represent the combination of the product of 3 parameters, which would include the damping ratio, the natural frequency, and the time T. Okay, and of course, once we set it, notice once we set the T here, then that will become our T sub S. So imagine this then becomes e to the minus x, but that x then would essentially be, you can say, well, once we plug it in and set it equal to a number and then solve for that condition, then that will become T sub S. So, so if you think about it from that viewpoint, this equation translates into that equation. Right? Right time to speak up if that's not clear. Because once you see that, then you realize it's just a matter of using your standard rules that you learned about possibly in calculus on how to solve for X. Okay, so all right, so the next step is just a kind of a standard procedure solving from X given that equation, maybe in algebra or trig, you learned about that. Anyway, so what do? You take the natural log of both sides, that removes the exponential dependence and just converts it down to a minus X. And then of course you have to do the same on both sides. That gives you the natural log of 0.02. Rewriting it as we see it here, hopefully you can see that. Puts a minus on the other side. Then, of course, properties of logarithms suggest you can write it that way, putting the -1 in the exponent. And then the 1 over 0.02 is 50, and I'll let you check with your favorite calculator that the natural log of 50 is approximately 3.91.
So when doing a 5% rule is the same steps?
Except for, instead of
Just
0.02, you use,
Yeah.
right, you know what it is. It's that basically, that's exactly what it is. Same steps, just changed to 0.02. Okay. Now, let's see, where are we? Okay, so we came up with our rule for the x, 3.91, right? So now we see that if we come back up to the few lines above, we see how x is defined in terms of t sub s right here. And that means we can solve for that product natural frequency t sub s, sometimes called the normalized time. And when we do that, it becomes x over the damping ratio. And so you're clear about this. The book gives us a rule for the 2% settling rule. And just to streamline the calculations, I think, it's the only reason I can see purpose of doing it, is instead of using 3.91, they allow us to use an approximation of 4. I won't make an argument about that. If that's what they want to do, I'm happy with that. But I want to make sure you understand that's where the 4 came from. It originally came from the 3.91. Any questions on that? Okay. Okay, so we got one example, and the thing you got to watch out about this this example is it's full of twos in a lot of places, and so it's easy to get confused. And if you're confused, bring up the point. But it's just the way the problem is worded. So anyway, so second order underdamped. It's all consistent with conditions we assumed, and we have to have a settling time of 2 seconds. Okay, now that just, okay, don't get too long. There's a lot of twos in this problem, just the way it's set up. Now find the damping ratio and the natural frequency required to meet this condition. Now when it says settling time of 2 seconds, he's also assuming that we're going to use another 2, the 2% rule, which is not connected to the 2 seconds, not connected to the overshoot necessarily. Those 2 other numbers could change. But it just happens that there are a lot of 2s in this number, and that's just the way it was written. Any questions on that? Okay, I'm not hearing any question on that. So I guess we'll see how this plays out. All right, so we're given some information. We're given the percent overshoot. We're given that we want a settling time of 2 seconds. So we've got a settling time of 2 seconds. And what we're supposed to do is, in a sense, work backwards and come up with the damping ratio and the natural frequency. Okay, in a sense, we're taking our formulas and working them backwards towards what we might have normally used as inputs, but I think it's a reasonable problem. So, any questions? Okay, so just to make it clear, our objective is to come up with a numerical value for the damping ratio and a numerical value for the natural frequency, and given what's numbers that are provided. Okay, now we've already established the first line as being correct. We'll see where that's helpful. So pretty much we can, the next line down is just repeating the same idea. So when we said the percent overshoot is 20%, what we're saying is this factor in front is 0.2, okay, 0.2. And that's where the first 20%, that's where the first 20% 2 comes in. Now you see the advantage in a way to this. I mean, you could argue, I'm not sure you had to do it this way, but I like it. And if you do it differently, it's up to you. The advantage is you're trying to solve for this, well, once you get this theta, okay, that angle theta, then we know that that's related to the damping ratio directly by just taking the cosine, just to let you know where we're going. So if we can solve for the theta, then we can solve for the damping ratio using the damping ratios to cosine of theta. So that's the idea is, well, if we can solve this for theta, then our half of the problem is going to be solved pretty fast. So let's see how that goes. So then with this formula, then we do kind of what we did before with the other problem. To get rid of the exponential, take the logarithm of both sides, it brings down the argument of the exponential, including the minus, and puts a natural log of 0.2 on the right-hand side. So we can solve for the tangent of theta just by rearrangement. I think I got all this, check my arithmetic on this, or algebra, I should say. And you would get, I believe you would get this. You can see that happening, right? So could you move this here, move that there, and you get this. Right. Now, you can pull out your favorite calculator again. We know that the natural log or a log of any number less than 1 is negative, so we're not surprised that the minus went away here, right? Because that's going to happen. I'll let you check. My guess is if you take the natural log of 0.2, you should get a minus 1.6, and then the minuses take care of each other. And you've got your favorite calculator there, you can check that. And you can also check that if you plug in these numbers, you get 1.95. So we're 60% of the way there. What we need to do then is to solve for the angle theta. I think that would be the more direct way to do it. So I'll let you check if you do the inverse tangent of the 1.95 number, then you can get your angles. If you select degrees, you get degrees. And if you do that, you should get, again, please let me know if you don't agree with your favorite calculator, approximately 63 degrees. Any questions so far? So now that we know the angle theta, we can solve for the damping ratio just by using the plug-in cosine theta, and it comes out to be 0.455. So in a sense, we now have solved for half of the information that's requested.
How is the damping ratio equal to cosine?
Well, that goes back a lot to the stuff we did in chapter 2. I don't know, I think on the equation sheets, you'll see that. Oh, here's a good one. I mean, if you go back to chapter 2, you'll see this figure appearing, this one right here, appearing in a lot of places. And even on the equation sheets.
Oh, okay.
So in a sense, I'm not able to completely reinvent the wheel here, but I can at least refer you back to where we're getting this stuff.
Okay.
I have a question.
Did I hear a question on that?
Yes, I have a question.
Okay.
Is this related to homework 5?
Let me see. Homework. I believe homework 5 was in fact the Roth criteria, wasn't it? Or am I hold on a minute. I'll tell you because I have it all. I have them here.
Okay.
Homework 5 was Roth.
Okay, then that makes sense. This has got to be related to homework 6.
Okay.
Yeah.
Okay, just wanted to be sure.
Yeah. No, homework 6.
Okay, thank you.
Can we talk about the assignments before we get off later?
Yeah, but why don't we do this? If we want to just, since we're sort of moving along here, let's finish this. The assignment, which assignment are we talking about? 6? We need to talk about.
Just some assignments in general, like due
like
dates or expectations or whatnot.
You mean procedure? You want to talk about procedure?
Yeah, just
Okay,
kind
well, I
of
want to make it
what
sure
we're going to be doing with all of that.
What I envision, since this seems to be working pretty good in terms of getting information back and forth, what I envision might be not all that different from how we were proceeding before. Let's say still would post solutions to homework assignments and then still open the floor to questions. But now that we can, it seems like this seems to be working, so maybe that part, we can do that over Zoom. And then, but I don't see practical to do in-class quizzes. I would still maybe make them kind of like, well, you know, you're on your own and you can upload them and then we can hopefully see them. I'll get them to grade.
Okay, yeah. I guess I was more leaning towards testing and stuff also.
Well, testing is going to be a little more of a challenge. In the sense that the tried and true methods, which I cannot claim I've put into action myself, but I understand they can work, would be some sort of, which would be one of two schemes, one of which, all of which seem to involve you having some sort of camera capability. There is some sort of feature through Canvas, something called ProctorU. And I have not been encouraged to pursue that one. And the other one is basically you're hooked up on with your cameras, and I can see you, and that's supposed to keep you on your honor, so to speak.
I think Proctor you have to pay for it though.
What?
I think you have to pay for ProctorU, but I'm not totally sure.
Well, actually, there's more than one version of ProctorU. There's a so-called an automated version for which it's supposedly free. And then there is actually live proctoring for which somebody would have to pay for, but no one that I know of is even considering that. So, and anyway, the ProctorU path is not highly probable at this point. The more likely scheme would be the one that it seems to be already been used within our college and our department, is where you just you have your camera turned on. I can see you while you're taking the exam, and I'm okay with that. That has to come down to that. Is that answering part of your question?
Yep.
So there are the other details that we'll talk about, but for the most part, that's kind of, I'm thinking I'm answering the part of the question you were primarily interested in. But if there's more, you need to ask. Oh, which brings me to a point. I don't know if you've seen it or not. I think I have it here. I'm asking you because I'm part of the, I'm learning all about this stuff right along with you. There's something in Canvas called Speed Grade, which allows me to evaluate electronically submitted assignments, even exams, electronically, so to speak, or right from within the computer, and then you can automatically see the markup. But I've never done it before, so there's two purposes. I'm asking you if you, and hopefully you've seen this. I can't really give credit for this, but I would like you to try. There's an assignment there, which I'm asking you to see if you can do a short upload. Short directions is create an electronic version of your page and see if you can upload it. And then I'm going to see how well that goes. Now, I would prefer, because it's going to come down to that, I prefer that you don't do it completely within, let's say, Word or PowerPoint, because that's not going to happen during an exam. I mean, during the exam, at least we may need you to, and even on quizzes, we may need you to upload your own handwritten materials. So somehow you've got to create a valid image of what is probably a hard copy. So I'm asking you to do this because for two reasons. Number one, it guarantees from your side that you know how to do it. And you can say, well, that's fine. You already know how to do it. But also it helps. But the point is, if you ran into a hitch when something serious has to be turned in, and it's not noted that you even tried to do it, and I don't think you have a legitimate claim, well, all of a sudden you've got a problem that you didn't deal with. Well, this is your opportunity to deal with the problem of learning how to upload things into Canvas before it becomes serious business in terms of allocating points. So if you don't do it now, and somehow the ball gets dropped when it's due, then and due to some technical problems on your side, then I'm going to ask myself, why didn't you do it earlier? So, and then also it helps me get a little bit familiar with the speed grade option. Is that any questions on this out there? Again, if you feel if you're 100% sure you're not going to have a problem, that's fine. But rest assured, if you run into a problem, I was told that contact IT. That's what they're there to help both of us, all of us. Okay, any questions, any additional questions? We're getting close to running out of time here, right? Or not? How close are we to running out of time?
Yeah, like 3 minutes
3 minutes over or 3 minutes to go?
to go.
Oh, good, okay, all right. So that means I can I finish? Let me see. I hopefully answered the important. Let me see if I can finish this one point, right? So let's just finish this one problem. There's only 2 lines at the bottom, and then we can say we're done with it. We can go to the next topic next time. So given, excuse me? So we know that the settling time is given as 2 seconds. And we're supposed to solve for the natural frequency. That's what's remaining to do. So we use our 2% rule, which is right there. And then we just, we put in for the settling time, we put it 2 seconds. Excuse me? What, something happened? I'm not hearing your question. Everybody still there?
Yeah, but I didn't understand what he said.
Yeah, he's cutting in and out right now.
Okay.
Yeah, it's just signal noise.
Is it better? I'm not sure where the problem is. Okay. So if you put in the 2 seconds, you put in the damping ratio that we found up here, and use the rest of the so-called 2% rule, you come up with, and check with me with your favorite calculator, 4.39 radians per second. And that completes that section. And for the record, we're going to start the next section on Wednesday, which, in case you're not aware of it, I believe it's section 5.6, and it deals with the topic. There it is. I'm not going to start it today, but here's my page of notes is ready for that. We'll be starting section 5.6 next time. Okay, so that's just to let you know. All right, I've got a couple extra minutes. I'll hang in here if you want to have questions. Otherwise, I think class. Yeah.
Can you repeat what you just said, like about a minute or two ago? I think everybody disconnected.
Oh, okay. So what in regard to what? And can you tell me anything about a minute or two ago? You mean the problem or the policy?
Whatever you just said, it was just about a minute ago. Just
okay.
Everybody disconnected.
Oh, okay. Well, so I all I said was you can solve for the natural frequency using the recipe associated with the 2% rule. Is that what you're talking about? That part?
I believe so, or
okay.
Maybe I was the only one that disconnected.
Okay. Well, the settling time that was given up here in the problem, 2 seconds in there. And the only thing you got to watch out for is all these 2s in here make it confusing, but that's the way the problem's worded from the book. And was it headed? I mean, was it a policy question? So if that was the case, I'm happy to repeat that too. I think what I also mentioned, we're going to start section 5.6 next time.
Okay.
So unless you've got another question, class is over, so to speak. I mean, you're welcome to go off and do what you have to do.
where are you going to be uploading the recording to? You going to put it in a file or something on the
I'll send out a
Canvas?
notice. I mean, after all, this is kind of like brand new. I mean, I didn't even know I was going to upload anything in the cloud until the guy came in and told me that's an option. So I'll have to lean on him to get this thing done. But he's around, so I guess I'll work on it, and then I'll send a note out when it gets uploaded. I think it should be possible to get it uploaded. The only thing is, I remember that to convert the recording to an MP4 takes a long time. I don't know why, but it does. So I was I don't know when it's going to be ready. When I say a long time, it's almost like, well, 1 hour of recording for 1 hour. 1 hour recording leads to almost like 1 hour of processing to get it to an MP4.
But later you plan on making it to where we can just record it ourselves?
Yeah, I mean, I don't really want to do it every time. I'd rather you guys do it.
Yeah, I'd like to have it.
If you want to have that option, I'll talk to them, make sure we get it clicked on so you can do it in the future.
Yeah, sounds
Option to
good.
record?
Yeah.
Okay.
Yeah,
It lets us. We just have to have that permission.
Well, that's what he said. He said he needs permission, but he told me right when he was standing here, he said, okay, we'd have to stop your meeting and restart it. And then, so that's when and then he said, well, another thing would be you could do it with the cloud. And so for today, that was our conclusion. So I'll let you know how that goes. This first time I've tried it. Did I get to the heart of your question? Hopefully.
Yep. Thanks.
Okay. Yes.
What about office hours?
I'm working on a plan. Right now, I don't have an immediate plan. I'm here right now if you have a question, but now that raises a good point. I would like to, let's do this. Because I always do it, open the floor to questions for, I believe it would be homework 5 on Wednesday. So we get that out of the way. I don't know, I'll put out a note on Canvas on that in case you're not still here. But does that seem reasonable? We can do that, right?
Yeah, that's fine.
Yes.
Homework 5, which is we're already past it. And it's got the Roth criteria problems. We probably should do that. I think I posted equations for that already. So I think we're good to go to do it when the time comes. So I'll come in prepared to deal with your questions, and we'll get that knocked out. And then I think we'll work the quiz situation kind of like we did with the last one. I'll post one there, and then you work on it, and then you upload it, and then it'll get graded.
Okay, that's fine.
Okay, and then yes, I'll be thinking about how to do office hours. I'm thinking it should be doable. I mean, in other words, for example, I just have to have a Zoom session set up, right? So you can optionally log in when you need it. And I don't see a problem with that. Anyway, I'll be thinking about it, just to let you know.
So the quiz 4, we can't upload until the 25th. Are you planning on just keeping that how it is?
Okay, so it says you can upload, and then I think the deadline is like the 28th. The deadline is Friday, but actually the upload process will continue for an extra day, I think. So in case you get it in late, I can give you some part credit, or most of the credit with slight deduction. And then at some point when I post a key, basically, which is intended, I think on either Saturday or Sunday, it shuts down and you can't upload anymore. Yeah, that's kind of how I think it'll work. But the idea is you hit the ground running on that one because you've already done this warm-up exercise and you know how to upload something into Canvas.
Dr. Pieper?
Yeah.
Do we have anything due on Friday?
Yeah, I believe, if I'm mistaken, what's due on Friday is this quiz that was handed out It's also posted on Canvas, unless I'm mistaken.
Okay.
And it says quiz 4, I think. That's due
Okay.
Friday. And then you can upload it, I think, a little earlier, if I'm not mistaken. But anyway, but the point is, it's actually due on Friday, and then I think on Monday we have that MATLAB eventually due.
Okay. Thank you.
Okay, it'll be a week from today. Okay. Any other questions?
Dr. Pieper,
Yeah.
for the sample assignment, do we just print it out, sign it at the bottom, make it
Yeah.
into a PDF, and turn it into Canvas? Is that it?
Well, yeah, I mean, it's intended to give you the confidence if you don't already have it, and it's giving me something to try with the speed grades and things. So, but yeah, that's what it is. You know, and it's there just to make sure that, which I know, human nature being what it is, unless you're asked to do something, you probably won't try it until you need it. And you know, there's certain technical difficulties come up for all of us. So I never have confidence something's going to work when it has to work.
Okay.
It's always good to try it before it has to work.
Murphy's Law.
Excuse me?
Murphy's Law.
Yeah, Murphy's Law, whatever can go wrong will go wrong, right? So anyway, any other questions? All right. Well, then I guess see most of you, not all of you, in a couple hours.
Is the link for signals posted online too?
Use the same link. I was told that there's nothing wrong with the way this scheme. In other words, that's that link. I'm planning on using it for both classes, the same link.
Okay, sounds good.
Okay. Any other questions? All right. Then I'm gonna sign out here, and I'll be back. I'm not going home yet. All right.